Hello, my name is Omar Al-Shunnag and here's my colleague Sami from Princess Sumaya University for Technology. We're going to solve this following question for stability circles in microwave engineering class. The question is, a gallium MOSFET has the following S parameters measured at VDS equals 3 voltages and IDS equals 30 milliampere for a 10 gigahertz frequency with a 50 ohm resistor reference. Now we're going to open the calculator and plug in the S parameters. S11 equals 0.52 with a phase angle of negative 145 degrees. S12 equals 0.03 with a phase angle of 20 degrees. S21 equals 2.56 with a phase angle of 170 degrees. S22 equals 0.48 with a phase angle of negative 20 degrees. Now we're gonna press on the basic data to calculate the K, delta and gamma in the input and output of the stability circles. We find that K is greater than 1, so it's unconditionally stable, which means that the amplifier is stable within the Smith chart domain. Therefore there is no need to draw them.
Now I'm going to solve the next part of the question to plot the 210 minus 1 dB input and output gain, constant gain, for the gallium arsenide MOSFET with the following S parameters as shown. So now we need to check the K value and delta to know the stability circles. From the calculator, we insert the S parameters to find delta and K. From the basic data, we find delta is 0.4 and K infinity. That means K greater than 1 and delta less than 1. We can see, which means it's unconditionally stable and the amplifier is stable within the Smith chart domain. There is no need to draw them. Now we will to calculate the gain for the source and the load, at which we can find the load impedance. For the source, the maximum gain equal 3 dB, and for the load it's equal 1.3 dB. For the source, we can draw 210 minus 1 dB constant gain circles, and for the load, we will draw anything is smaller than 1.3 dB. 1 minus 1 0 can be drawn. Now we need to insert the 2 dB for the constant gain circles for the source in the calculator. To find the radius and the magnitude of the center, the phase is conjugate to S11 phase 155. Now we use Kitab and draw the we first draw the phase. By using the pen, we will going to draw the line. After that, we will going to find the magnitude of the center. From the calculator, we find that the magnitude is 0.625. Use a compass. From the coefficient scale, we open it 0.625. And now draw the center. Now we need to know the radius. Radius 0.254. At the same scale, point 254. From the center, we draw the 2 dB constant gain circle. We do the same for 1 dB. From the calculator, we insert 1 dB and find the radius and the magnitude. The magnitude is 0.546. From the center, now the radius 0.374. Now for 0, the radius and the magnitude are the same. Back to the kitab. The radius are the same. We do the same for the 1, 0, minus 1 dB, and now we are done with the source. We do exactly the same for the load, and we get the result as follows. And this is the gain circles of the load. Now we need to find the matching network that gives the maximum gain for the source and the load. We need the calculator. We insert here 3 dB, and for the load 1.3 dB. We can see the radius is 0, it's a point. The magnitude is 0.7. The same for the load. The radius is 0, it's a point. That gives us the maximum gain. Back to the kitab. From tools, compass. You open it by 0.706. This is the constant gain circuit for 3 dB. We do that for the load, same, it's the same. This is the 1.3 dB. Now for the matching network for the source, we are going to follow the constant resistance circle with intersection with the inductance constant circles. On the resistance circles, we added a series inductor. Now for the matching network for the source, we are going to follow the constant resistance circle with intersection with the inductance constant circles as shown. Now from on the resistance circles, we add a series inductance, and on the conductance circles, we add a parallel capacitor. The series of the matching network of the source is a series inductance and parallel capacitance. This is for the source. Now the matching network for the source for the load, we are going to follow the constant inductance circles counterclockwise with the intersection with resistance constant circles. On the inductance circles, we adding a parallel inductance, and for on the constant resistance circles, we add a series inductance. Sorry. The matching network for the load is a parallel inductance with a series capacitance. For matching network for the load, we are going to follow the constant inductance circles with the intersection with the resistance circles. On the conductance circles, and we follow counterclockwise, we adding a parallel inductance. This is the intersection with the resistance circles. Now we adding a series capacitance. The matching network for the load is a parallel inductance and series capacitance. To find the load impedance for maximum power gain, we subtract A2 from A1 NY and subtract Z from A2 NZ. We do the same for the source to find the source impedance for maximum power output. To find the load impedance for maximum power gain, we subtract A2 from A1 NY and subtract Z from A2 NZ. And we do the same for the source to find the source impedance maximum power gain.